Okay, so these are our water notes that we were going to go over today. Please follow along. Water is a polar covalent molecule with strong intermolecular forces. Going back to end of October, 1st of November, remember we learned that all molecules have, or all covalent compounds have, London dispersion, and then the polar covalence, when we have that hydrogen, we have hydrogen bonding with oxygen. So this polar covalent, remember the oxygen is slightly negative because there's an unequal sharing of electrons between the hydrogen and the oxygen, so the hydrogen is slightly positive. Then we have the hydrogen bonding between the slightly positive hydrogen and the slightly negative oxygen. So this is what it looks like, these intermolecular forces. The unique properties of water all occur because of the hydrogen bonding. We saw several times that the water is a universal solvent. It's very polar, therefore it dissolves polar and ionic compounds. The rule, remember, is like dissolves like. It's called the universal solvent because it dissolves more substances than any other liquid. Let me zoom in a little bit more. That's too much. Okay, so it has a high surface tension. This surface tension is caused by those intermolecular forces that act inward. The interior particles or interior molecules are attracted to each other in all directions. The surface particles or molecules are only attracted inward, so the surface of the liquid is pulled into the spherical shape. And you saw that on the wax paper yesterday. And you also saw that surface tension when I poured the jar upside down with the screen and it didn't pour out. This high surface tension is what gives us a red belly when we hit its splat. It's what allows bugs to lay eggs on the surface. It allows for quite a few applications. The low vapor pressure of water allows the water molecules have cohesion, which is the attraction between like molecules. This does not allow them to become a vapor easily or a gas, so it has a low vapor pressure. Remember cohesion, that's why you couldn't break those water molecule or those water bubbles when they were water droplets. I'm sorry, that's what I was trying to say. You couldn't pull them apart real easily. Another unique property of water is the high specific heat. This is the amount of heat that must be added or removed for the temperature to change. Think of concrete versus a swimming pool. The concrete is going to be hot and it's going to be exposed to the same amount of sunlight as the water was. Yeah, the concrete is a lot hotter because it took less energy to change the temperature. Whereas the swimming pool, the water is going to take a lot more energy to increase the temperature. So concrete would have a low specific heat and water would have a high specific heat. Water actually has a high melting point compared to many other compounds, covalent compounds. This is 0 degrees Celsius and boiling point's 100 degrees Celsius. Density is another unique property. Most solids will sink in their own liquids because as they freeze, the molecules actually come together and get closer. We're same mass but less volume, so they become more dense. However, water has its greatest density at 4 degrees Celsius. It's still in the liquid phase. Below this temperature, water becomes less dense because of the hydrogen bonding, holds the molecules in a liquid 3D shape with spaces in between. This results in the same mass having more volume, therefore it's less dense. So ice, which is solid water, floats on its own liquid, which is water. So here you can see the liquid water, how it's doesn't have as much volume. And here, because of the hydrogen bonding, there's a lot more space in between the particles. So applications of water's unique property: because of the high surface tension, some insects can lay eggs on the water. Because of the high specific heat, coastal areas, which means near water, have a moderate climate, doesn't change very much. Because ice is less dense then water ice will float on top and the water below is somewhat insulated and a bit warmer. This allows plants and animals to survive. Now I know I went over this all really quick, so hit pause at any time that you need to. Okay, so how does an ionic compound dissolve in water? Remember, like dissolves like. So polar dissolves polar or polar dissolves ionic because these guys have charges. So an ionic, remember, is a metal and a non-metal. So let's use lithium chloride as an example. Lithium chloride will separate into the ions lithium +1 and chlorine -1 when dissolved in water or when put into water. We call it dissociation. Recall, water has a slightly negative oxygen and 2 partially positive hydrogens. The water molecules will rearrange themselves around the charges so that opposites attract. So if we have a lithium +1 and a chlorine -1, those water molecules will actually change. You can see, whereas the hydrogens are here, they'll actually change around so that way the oxygen is attracted to the positive cation and the hydrogens will be attracted to the anions. Okay? Like I said, hit pause so you can catch up. So let's talk about colligative properties on this video as well, so that way we'll be done. A definition of a colligative properties are properties which depend only on the ratio of the number of solute particles to the number of solvent molecules in a solution. Think molality, molarity, etc. And we'll talk about those at the very end of this lecture. Okay, so ionic compounds will dissociate into ions, therefore producing more ions. Covalent compounds do not dissociate, so we're not concerned about covalent compounds when we talk about colligative properties, because the more ions they are, therefore a higher number ratio, then the properties will change. So which of the following would have the greatest effect on colligative properties, such as vapor pressure? I don't know why I crossed that out. Let's leave it at colligative properties. Aluminum chloride would and nickel carbonate, nickel 2 carbonate would, because these guys are ionic compounds that dissociate and ionize. This guy would not, because benzene would not, because it, actually that's not benzene, that would be benzine, would not because it is a covalent compound. So there's many different types of colligative properties. I'm going to teach you 3. Just know the basic definition. We have freezing point depression, which describes the temperature difference between the actual freezing point of the pure solvent and the temperature at which the solution actually freezes. So the freezing point depression describes the temperature difference between the freezing point of the pure solvent and the temperature at which the solution freezes. The boiling point elevation. This describes the temperature difference between the boiling point of the pure solvent and the temperature at which the solution actually boils. Remember, freezing point is when we go from a liquid to a solid. Boiling point is going to go at the surface where we go from a liquid to a gas. Now, vapor pressure elevation. This should say elevation. The vapor pressure of a liquid is the pressure of the vapor which is in equilibrium with the liquid. And so it's going to change, all 3 of these actually will change based on the amount of ions. So an equal number, let's answer this question. Again, go ahead and pause if I went too fast. I'm trying to keep this under 10 minutes. An equal number of moles of potassium iodide and magnesium fluoride are dissolved in equal volumes of water. Which solution has the higher boiling point, vapor pressure, or freezing point? Well, let's see which one has the greater number of ions. So potassium iodide will decompose or ionize into potassium +1 and iodine -1. Magnesium fluoride will decompose or ionize into magnesium +2 and 2 iodines. So this has 3 parts and potassium iodide has 2 parts. So magnesium fluoride will have the higher boiling point, the higher vapor pressure, and the higher freezing point because there's more ions in each. Now, I should have written this part at the very top, but go ahead. These are just some definitions of concentrations of a solution. These guys can be expressed in molarity, which we've already learned. This is moles per liter of solution. Then we have this word molality. So we had molarity, molality. This is moles of solute per kilogram of solvent. This is liter of solution, now that we're looking at kilogram of solvent. And then we have percent by mass. Percent by mass. This is mass of a solute divided by mass of a solution. You know, I'm not going to test you over these. I just want you to write them down and understand them. Okay? Again, email me if you have any questions.